So we have already discussed about scalar triple product. So today we are going to discuss about the geometrical interpretation of scalar triple product. Okay, the physical significance. Okay, so this topic is about the geometrical interpretation of scalar triple product. So here we have something called as parallelepiped. Okay, a three-dimensional structure. So here the three edges, which are called as the coterminous edges of this parallelepiped, they are represented by the vectors A vector, B vector and C vector. You can say the length, breadth and the height. So here the OA edge, it is represented by A vector, the OB coterminous edge, that is represented by B vector, and OC vector, that is C vector. Now we know that the scalar triple product, it is represented as A vector, B vector and C vector, which can be written as here A vector cross B vector dot C vector, or A vector dot B vector cross C vector, whichever way we want to write. Now if we consider this way of writing, here the cross product or vector product of A vector and B vector gives us this A vector cross B vector, which is perpendicular to the plane containing A vector and B vector, that is this plane. Okay, this plane, it is perpendicular to that, this A vector cross B vector. Now here A vector cross B vector, it represents the area of the base of the parallelepiped. Okay, the area of the base of this three-dimensional structure. Now here A vector cross B vector dot C vector is A vector cross B vector modulus, then C vector modulus, then cos theta. So here theta here is the angle between the resultant cross product A vector cross B vector and the third coterminous edge of this structure, which is this here. Okay, this angle theta between A vector cross B vector and C vector. So here C cos theta, okay, C vector modulus cos theta, we can say is the projection of C vector in the direction or along A vector cross B vector, okay, which is the area vector or the area of the base of the parallelogram. So we can say this is in a way is equal to the area of the base of the parallelepiped okay, this into the height, and area into height, that gives us volume of the parallelepiped. So simply, whenever we have a parallelepiped given in terms of its three coterminous edges represented in the form of vectors, be it in this form a1 I cap plus a2 j cap plus a3 k cap, then b vector given as b1 I cap plus b2 j cap plus b3 k cap, and c vector given as c1 I cap plus c2 j cap plus c3 k cap. The volume of the parallelepiped is the scalar triple product of a vector, b vector, c vector, which is equal to a vector dot b vector cross c vector, or a vector cross b vector dot c vector. Okay, anyway, if you do this in this way, b vector cross c vector, then b vector cross c vector, the area of here OCFB, that will become the base, and in this direction there will be the height. So same result we will get. So this can be represented in determinant form as we calculated the scalar triple product A1, A2, A3, B1, B2, B3, C1, C2, C3. Okay, this. So this is the geometrical interpretation giving us the physical significance of scalar triple product, which gives us the volume of a three-dimensional structure, which is in this case a parallelepiped. Okay,